Hello everyone, I am Bhavya Ghai from Stony Brook University and today I'll talk about our paper Fluent. Fluent is an AI augmented writing tool for people who stutter. Stuttering is a speech disorder which impacts more than 70 million people worldwide. Common signs of stuttering includes disfluencies like repetition of a sound, prolonging a sound, pause or blocks, etc. On the personal front, stuttering can lead to anxiety, frustration, embarrassment, public stigma, and self stigma. On the professional front, people who stutter might be perceived as less capable and less employable than their peers who do not stutter. Speech therapy can be helpful in managing or living with stuttering. However, access to therapy can be limited and might be associated with blaming and shaming. Unfortunately, there is no cure for stuttering. As a person gets older, they become more conscious of their condition and learn to anticipate stuttering moments better. When an individual anticipates a stuttering moment, they use different strategies to conceal their condition, which are known as avoidance behaviors. This may include using fillers, substituting the feared word with its synonym, talk around the feared word, etc. Research has shown that all people who stutter use such strategies to some degree. A recent study found that the objective of 69.5% of people who stutter was to hide their stuttering. It should be noted that anticipating stuttering and managing it can cause additional stress and burden. In this work, we are trying to reduce this burden and we have focused our work on word substitution. Our contributions. We devise a novel method which can identify words that an individual might struggle pronouncing. We design and implement a new writing tool, Fluent, which embodies our approach to identify difficult to pronounce words and then suggests suitable personalized alternatives. We evaluate our system by measuring its ability to identify trigger words for 10 simulated users. So, how do we identify difficult to pronounce words? Research has shown that people are likely to stutter on some words more than others based on their underlying phonological patterns. To capture the phonological aspects of different words, we have used phonetic embeddings, which are based on CMU's pronouncing dictionary. Phonetic embeddings provide high dimensional vector representation for a word such that words with similar pronunciation lie close to each other in the high dimension space. In the beginning, we ask a user to provide two sets of words that they find easy and difficult to pronounce, respectively. Each word is mapped to its corresponding phonetic embedding, and thereafter we train a binary classifier to differentiate between easy and difficult words. Each person who stutters might struggle on different set of words, so we need to train a different classification model for each user. Typical supervised machine learning models require large amount of labeled training data to provide good results. Asking each user to provide hundreds or thousands of labeled data points upfront can be too cognitively taxing. Here, data points refer to the words which an individual finds easy or difficult to say. To circumvent this issue, we used active learning. Active learning is a learning paradigm which focuses on training effective ML models using a minimum number of labeled training instances. At the outset, active learning requires few labeled data points, and thereafter the model keeps evolving iteratively by leveraging user feedback over time. Let's see a demonstration of how our system actually works. This is the visual interface of Fluent. It is designed to look like a normal text editor. In the beginning, the user can go over the top right and provide a set of words which they find easy and difficult to say. Here, the user finds words which have R sound as at the second place, difficult to say. Moreover, the user can also choose a confidence threshold. Here, the system will only highlight those words whose likelihood of being difficult is 70% or more. Then the user will click on the update button. Now the system will analyze all the words in the interface and highlight words based on the seed words and the confidence threshold. The user can now go over any word and choose a particular alternative, or choose to even ignore this suggestion altogether. On choosing any of the alternatives, the model will keep refining itself. This is called implicit feedback. The second way to provide feedback is explicit feedback. For that, let's go over the top right again and choose the refine model button. Now the system will keep asking a set of questions that does the user find a particular word difficult to pronounce, and the user keeps giving a yes or no answer for every question. The hope is that as the user interacts with the system more and more and provides feedback, the system will be able to learn the personalized needs of the user better and better over time. Coming to evaluation, we have evaluated our tool from a machine learning perspective. We modeled 10 different users based on self reported data from stuttering communities on Facebook and Reddit. Each simulated user is characterized by a phonological pattern that they struggle pronouncing. For example, a user might struggle pronouncing words which start with ST or FL sound. We used over 2000 TED Talk transcripts to test our tool for these 10 simulated users. We simulated two scenarios, that is, when a user provides solely implicit and solely explicit feedback. For each feedback scenario, we computed and recorded metrics like F1 score, accuracy, and precision after every interaction. Our objective is to evaluate how well our approach can learn users' needs. Coming to results, these three plots show the mean values for precision, accuracy, and F1 score for the 10 users across 500 interactions. We can observe an overall positive trend for both forms of feedback across different metrics. In under 20 interactions, our classifier reached a mean accuracy of over 80% for both forms of feedback. A random classifier would have yielded just 50%. It is also interesting to observe that explicit feedback is more effective than implicit feedback and random sampling across different metrics. So the user should try and give explicit feedback whenever possible. Overall, these results validate the theoretical capability of Fluent to learn users' need. In conclusion, we present Fluent, the first AI augmented writing tool for people who stutter. Future work might explore the usability, utility, and effectiveness of this tool from a human centered perspective. Future work might also devise design guidelines to inform the development of such tools in the future. Please check out this GitHub link for more details about this tool. We have made the code for this tool publicly available. With that, I thank you all for your attention.